Howdy folks, welcome to the first part of lecture 29 in MAT353, I mean to say. So again, I am actually posting this on the 22nd of April, but this is the lecture that was scheduled for the 21st of April. I'm going to try to get caught up and to have all of this worked out by the end of the week. So I'm going to try to get the lectures straightened out by then, and then we'll be releasing them on the date that they're due before the day that we normally would have met. I do apologize for not being able to have had that done so far. I am doing my best, I assure you. So the first thing that we're going to talk about today in the first part of the 29th lecture is the last topic that I want to discuss regarding multivariable integration. This is not something I'm going to test you on, but it can help to deepen your understanding of the kind of thing that we're doing here. And this is going to be a brief discussion of the change of variables formula, or the change of variables theorem. The core concept here is that sometimes hard problems can be made into easy problems by changing the way that we view space or the way that we measure space. So you take an unruly looking integral like the one shown here at the bottom. This is the integral of x sine of x squared. So the fact that we have this sine of x squared in the denominator means that the sine function is going to start to oscillate faster and faster as x increases. It's not going to... Sine sees space not as the x-axis, but as the square of the x-axis. So the difference between 7 and 8 is 1, but the difference between 7 squared and 8 squared is much larger than that. So because sine is seeing its spatial input squared, as the x value gets larger, sine is going to start seeing larger and larger increments for every actual increment on the x-axis. Sine's going to think that as we move from 7 to 8, its input is moving from 49 to 64, for instance. So that's why you start to see the increased frequency of oscillations in the graph below, and also the extra factor of x sitting in the integrand is going to mean that the peaks and valleys of this sine function actually increase in magnitude. Oh, excuse me, folks, as we move down the x-axis. So we see these oscillations occurring more and more frequently and also becoming more and more extreme. So that's fairly strange and nasty looking. When we perform the obvious U substitution here, this is an ideal candidate for U substitution. When I make the appropriate U substitution, which is shown here, I am effectively changing the variable. I'm going from my x variable to this new U variable, which is x squared. And what that serves to do is basically flatten space in the way that sine sees it. We no longer see this increased frequency of oscillation. And in fact, the extra factor of x in our du expression, du being x dx, or 1/2 du being x dx, that also serves to counteract the increase in magnitude of the oscillations that we were seeing previously. So by moving from the x-axis to the u-axis is our horizontal axis. I meant to label this horizontal axis here u, that is the u-axis. We still see the y-axis in the vertical direction, but this is now the u-axis, not the x-axis. The relationship between those two spatial environments is given here, and to a lesser degree also here, but it serves to sort of stretch out. So over here on the right hand, where these oscillations were occurring more and more frequently, we're stretching that space out in such a way that we see even oscillations, even and regular oscillations now. So the area over here didn't need to get stretched as much, but as you move along the x-axis, you do have to stretch it out more and more so that you see this evenness to the oscillations. So that's the idea. Like, you can sometimes take a problem that's sort of ill-fitted for the space that you find it in, and you can change the way that you view or the way that you measure space, going from the x-axis to the u-axis here, and in so doing, you can flatten things out. You can sort of turn something that was sort of wily and nasty and behaving in unpredictable ways, and you can give it more of a regular character by changing the lens through which it's viewed, the set of variables that we use to approach the problem. And I know I'm speaking very generally. All of this relates to much higher level concepts than we're going to go into in detail in this course, but we can tie some things that we've done previously together, including U substitution, which we're talking about now, and so it is worth mentioning it in order to facilitate and foster a better understanding of some of the deeper principles that we are making use of in this course. So that is a clear picture, or this is a picture of U substitution, and it is not often in classes prior to this that you get a picture of u substitution this way. It tends to be more of a formulaic thing that we do. But the idea that this picture becomes this picture as you move from your x variable to your u variable, that's why u substitution works. That's why it's useful to us. And what we are literally doing is changing sort of the scale on which we view the horizontal axis. And we're not even changing it in a regular way. We're changing different parts of the horizontal axis in different ways so that we can achieve a much more pacific picture here, a much more docile function that we can integrate. So the actual change of variable that we're performing is u equal to x squared. There's this other aspect of u of substitution where you have to find your du expression, and that accounts for the way that we've stretched space out and changed it. So when you do make these types of alterations to space to turn hard problems into easy problems, you want whatever result you find in your new altered space to be applicable to the original problem. And in order for that to be the case, you have to keep up with the way that you're stretching or compressing space in different regions so that you can translate the results from the new space back to the old space. You sort of have to keep a roadmap of how you got from one to the other and in order to be able to get back again. And that's exactly what this expression gives us in some sense. This is the expression that accounts for the way in which we have had to modify the ways that we measure space in order to make the results that we find in our new space still relevant and applicable to the problem that was originally posed in the old space. Again, I recognize I'm being vague. These are high-level concepts. This would be something like, to deal with this in a careful way requires much more mathematics, but because we're making use of it and we can draw some analogies together, we can at least outline what's going on here, and that's all I intend to do. And we have an unfortunate line running through the remainder of these pages. I apologize for that. I will try to clean my scanner, but we are going to proceed, so bear with me here in the interest of saving some time. So let's talk about change of variables more generally. In R1, it's just u substitution. So the example that we just went through is a good example of what change of variables looks like in R1. In higher dimensional spaces, the different coordinate systems that we have studied are exactly different changes of variables. So going from rectangular to polar in R2, that is a change of variables. Going from rectangular to either cylindrical or spherical, those are both changes of variables in R3. The general pattern, or the general theory, says that if your x variable is some function of u and v, and your y variable is some other function of u and v, then your dA expression in rectangular, which is dx dy, becomes this matrix times du dv. This is what's known as the Jacobian. There is a change of measure section in Stewart, so you can have a look there for some greater detail, but this is known as the Jacobian, named after a guy, so capital J in Jacobian. But you take the partial of x with respect to u, the partial of x with respect to v, partial of y with respect to u, partial of y with respect to v, and we are taking the determinant of this Jacobian matrix. So the idea here is that, like, how does our x variable change for a change in u? How does our x variable change for a change in v? And likewise, y with u and y with v. This is giving us a measure of how these two, the xy and the uv planes, how do they relate to each other? If I move a little bit in the x-plane, what kind of movement corresponds to that in the uv plane? And likewise, if I move my y variable a bit in the x-plane, or counter, I suppose, actually this is the partial of x with respect to u and y with respect to v and so forth. So if I increment my u variable a bit, what sort of change does that result in the xy plane? And if I change my y variable a bit, what kind of change does that result in the xy plane? So this connects the two, this kind of a Jacobian matrix. It shows us the way that the xy and the uv plane are linked up. And it has the information about where did space get stretched as you move from xy to uv, where did it get compressed, and how is it that we take all of that information into account. So a quick example, this is where the r dr d theta comes from. Going from rectangular to polar, x is r cosine theta, y is r sine theta. We talked about that, drawing some pictures and thinking about right triangles. That means that dx dy should be, here I'm taking the partial of x with respect to r to get cosine theta. Here's the partial of x with respect to theta. Here's the partial of y with respect to r, and y with respect to theta. If I actually compute that determinant, I'm multiplying down the main diagonal, subtracting off the product of the off-diagonal entries. I get r cosine squared plus r sine squared, factor the r, simplify, and I've got r dr d theta. So this expression comes from the change of variable formula. Similarly in R3, if you've got x as a function of 3 new variables, y as a function of 3 new variables, and z as a function of 3 new variables, these are g, h, and j, apologies for the typos, then the dv expression, which in rectangular is dx, dy, dz, in your new coordinate system in terms of u, v, and w, you're going to have this larger Jacobian. So across the top we've got x and its partials with respect to the 3 new variables, y and its partials, and z with its partials, du, dv, dw. We can do the simple example here, which is cylindrical, where x is r cosine theta, y is r sine theta, and z is just z. So z and w are the same in this notation. Then we have these partial derivatives. There's a bunch of zeros because some of these functions don't depend on some of the variables. And you can take the 3x3 determinant here, just like we do for cross products. So I'll have the first entry here in the top left, and then the determinant of this 2x2 submatrix minus the second entry, and you get this 2x2 submatrix where you delete the middle column and so forth. And if I work through that calculation, I'll get r dr d theta dz, which is the dv expression in cylindrical coordinates. It works for spherical as well. So the whole Jacobian matrix is much more involved. It's a more elaborate calculation, but feel free to have a go at it. It's not difficult. It's just a matter of housekeeping and some simplification using the most famous trig identity, the Pythagorean theorem. But this is where these different coordinate systems come from. They are exactly changes of variables from rectangular coordinate systems. And this is why I have said in the past that there's nothing special inherently about the cylindrical or the spherical. There are in fact infinitely many different coordinate systems. The cylindrical and the spherical are two famous ones, as is the Cartesian, a famous one. But you can create whatever coordinate systems you like. There are some requirements. You have to have your functions be continuous and non-decreasing, and there's some technical constraints that you can have a look at in the section on change of measures. You effectively need what is known as a bijection, at least almost everywhere, is the way it would be said in a more advanced course. But in general, there are a multitude, in fact infinitely many different coordinate systems, all of which are given by the change of variables formula. And in fact, change of variables is just a very special case of a more general theorem known as the change of measure theorem. So it all has to do with the way that space is measured, and we can sometimes change the way that space is measured. The change of measure theorem is very important. It shows up all the time in my own research. It favors heavily in theoretical probability, in a subject called stochastic processes, and because of that it shows up in a fairly significant way when it comes to mathematical finance as well, if that's something that you're interested in. That's the context in which I've seen it. Much of my work in mathematical biology mirrors work that's been done in mathematical finance, and so we see some of the same phenomena, and certainly the change of measure theorem factors heavily in these fields. Alright, thank you folks. We will reconvene and move into our next topic, which is going to be vector calculus.